Thank you, Allie. Allie. Hey, what are you doing? You're not helping the class. Thank you, Allie. Enjoying having you here. Hi, Eddie. I'm not sure how to pronounce your name, but I just said Addie, so. My cat just invaded my cordoned off area and is helping me with my Zoom meeting. Thank you, Allie. You're being very helpful. Nobody wants to see that. Nobody wants to see that, girl. You got about 3 more minutes before class starts for the actual time, so just chill out there. But if you have any questions, feel free to ask me. Do you have a speaker, Addie?
Yeah, I do. It works fine.
Okay, cool. Meet Allie, my cat.
She's very cute.
Yeah, it's kind of doesn't make it any easier. Allie. I also have a really adorable little Chihuahua, which I've never liked Chihuahuas before, but this one kind of caught us off guard. I'm sure he's going to visit y'all at some point. Why can't you just sit on my lap like a normal cat? You live in this area, Addie?
Yeah, I live in Edenton.
In Edenton? Okay. I'm a graduate from COA myself. I went to Currituck, and then when I graduated, I'd done so well, they told me they weren't quite finished with me and I needed to go to COA first. So it actually turned out to be a really great experience for me.
Yeah, I used to go to Currituck, but I moved to Edenton.
Oh. It's a lot slower out there even compared to Currituck, huh?
Oh, yeah.
Do you have any questions about any material or any of the syllabus stuff before we get started?
Not yet, but I'm sure I will once the course gets harder.
Yeah. It is an online class, so it's not necessary that I'm going to necessarily be able to get lectures up, but I'd like to at least put a lecture up a week, and maybe even more. So hopefully that'll help you as well. But if I take the time to put them up there, you probably want to pay attention to them because they'll probably involve some things that wasn't as clear. I try to pick out the stuff that I think is important that the book doesn't necessarily explain that clearly. So that's what I choose to put in videos often.
All right. Thank you.
You're welcome. So far, it looks like you're the only one showed up. I'll give them a few more minutes. All right, well, I'm going to go ahead and start. I appreciate you coming, Addie. It is not mandatory that they come, so I certainly understand them not showing up. But I mainly, I mainly wanted to have these meetings so we could start off having any questions that might arise or anything like that. And I figured I could also use the time. I'd go ahead and do a real-time lecture discussion of it. And if I have an audience, that makes it even better because they, pretty much students always want to ask the same questions. So it would certainly be helpful. Feel free to just speak up if you have any questions. You can unmute your speaker and speak up. You don't have to, raise your hand or anything like that. But just to clarify, you don't have any questions for me about any of the syllabus material. You said earlier you didn't, or about any of the assignments or the material itself. All right. Well, I put this week, there's an assignment for everybody to try to watch Beyond the Big Bang. Was sort of the season finale of season 1 of the Universe series. That's a History Channel thing. So if you have the History Channel, like through satellite or cable, then you can go to that streaming site and put in your cable provider or your satellite provider, and they can verify whether or not you or your parents or whatever have that account, and you can watch it for free. Like I said, some libraries have it. You might be able to find it on Apple TV and Amazon Prime, all sorts of stuff like that. If you have to buy it, you don't have to watch it, okay? If you've got the opportunity to watch it without buying it, then by all means, I would go ahead and do it because I'm working on it, getting basically copyright allowance to show it on my private Canvas page. So that might take a little while. I just got an email back from them today, and I got to take another step towards that. But that's going to come up. It's a wonderful video. It's more or less like a documentary on not only on the entire course that you're taking now, but just basically on the history of astronomy. So it starts off talking about what the Ptolemaic model handled, how the ancient Greeks thought, what they knew versus what they didn't know, all sorts of stuff like that. Then it goes all the way up through basically a priest predicting basically the Big Bang. So you'll hear these stories that Big Bang came from the depths of hell and stuff like that, when in fact it was actually a priest that was one of the first people to actually suggest it, and he suggested it based on Einstein's equation. So it's a very interesting video. It's literally probably 80% of what we cover in our course is at least talked about in that class. In that video. So it's a little over an hour and a half, I think. But if you can watch that and do those questions, that's awesome. If you can't, don't fret it right now. I'll eventually figure out a way to put it up, and if that happens, then you can watch it for free. So the next thing we're supposed to talk about, by the way, that does mention the Big Bang, and I want to give you some information about that. So a lot of people have this misconception that the Big Bang is basically that all the space in the universe existed and there wasn't any matter or anything. It was just big empty space, and that there was a CB point at which all the space blew out of. That's completely wrong. That's crazy, but it's completely wrong. Most people think that's what the Big Bang is. That's what I thought it was when I first heard about it. And it's actually way even weirder than that. It's so weird that the space itself didn't exist, because the Big Bang created the universe, and the universe, and this is why I stressed that definition when I talked about universe earlier, the universe is all the matter, all the energy. Now what we know of is all the dark matter and all the dark energy, and the space itself all combined. That is the universe. So when the Big Bang created the universe, it actually created the space itself. So the space itself, which we don't necessarily think's inside of anything, came out of nothingness, infinitesimally small nothingness, blew up and just gets bigger and bigger and bigger, and we're sort of inside of that space. But that space is not necessarily inside of anything bigger. That's the weird part. So if you think about the Big Bang and it's not really hurting your head, you're probably not thinking about it enough. It's a really, really, really abstract concept. And oddly enough, it was suggested by Einstein's equations, and there was a Russian guy that actually beat Lemaitre to it. I predicted it as well, but they were in sort of the backwaters of science at the time, so we didn't know about that. But anyways, two separate groups predicted it as a ramification of Einstein's equations. And then lo and behold, a guy by the name of Edwin Hubble actually made observations that more or less would have forced the idea of the Big Bang on us anyways, because there's no other way you can interpret it. Because what he saw was that if a galaxy is 2 megaparsecs away and it's moving at 100 meters per second away from us, if another galaxy is 4 megaparsecs away, that one's going to be moving 200 meters per second. If another one's at 6 megaparsecs, or let's say 8 megaparsecs, that one's going to be moving at 400 meters per second. So the farther you go, if you double the distance away, you double the speed at which that galaxy leaves you. And we only understand that in terms of not galaxies moving through space, but the space itself expanding between them. So the normal model is, let me show you a little idea of what a normal model of that looks like. I'm going to turn it to my document cam and get a fresh sheet of paper. So what we normally think of when we think of the Big Bang is we try to think of this, let's get this up here, make sure I can focus on the screen. I think I have to do, not that one. There you go. Okay, I just need to make sure this is focused. That looks pretty good. Okay, so you think of like raisins in a raisin bread. So this might be our galaxy, that's a raisin. And then we go over a distance to the right, and there's another raisin. So this one's us. Then they go the same distance to the right, and there's another one, and the same distance to the right, there's another one. Same thing on this side, same thing on this side, same thing on this side. And then, of course, for each one of those, there's another one here, 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 and then another one here, 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 another one here. So imagine these as little raisins in a raisin bread. Well, as the raisin bread is set out, so you mix up the batter and you put the raisins in, these are obviously very uniformly set up raisins, but that's for a good reason. But we put them up uniformly like that, and you just sit it out, and it slowly would just expand. It's just going to get bigger and bigger and bigger and bigger. And when that happens, what you'll see is this space right here. Let's say this thing doubles. Well, if that's the case, then here we are now. And now this one, instead of being 1 distance away, is twice as far away. So is this one. So it'll be over here now. So is this one right here. It'll be, in fact, all the way over here now. And this one will, in fact, be all the way over here now. Actually, a little bit further out, like that. Okay? The same thing will happen to these guys. So this one will be about twice as far away. So I'm going to say it's roughly this far, and this far, and this far. Okay? And this one, 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 and this one. Now this might look odd, but that's what happens when this thing doubled in size. So check this out. If we're here again, so this is us, what we see is this galaxy right here has went a distance of, let's say this was 1 parsec before, so 1 PC before. Now it's 2 PC. Okay, so that's 2 parsec away. And let's say the time span has been a year. That would suggest this thing is moving with a velocity of 2 parsecs per year. But check this out. This guy right here was 1 parsec from the one next to him, and that one was 1 parsec from us. So it was 2 parsec, but now it's 4 parsecs because this is 2 parsecs as well. So this one moved at 1 parsec per year. But this one over here actually moved at 2 parsecs, or excuse me, it was 2 parsecs away. Yes, and now it's 4 parsecs away, so it went to 2 parsecs per year. And not only that, if you pretended you were this guy over here, you'd get the same results for all the other ones. So it's not only that everybody's moving away from you, but everybody's moving away from everybody else. And there's no real center. It's like everybody's the center. Or you can imagine doing the same experiment, draw these dots like this on a balloon that you've blown up with air just barely, and then blow it up until the distance between two adjacent ones is, say, twice as big as it was before. And you'll see that each of the other dots, when you go twice as far away, they'll have moved twice as far, and therefore their speed is twice as fast. So that's why we have to not envision the actual galaxies moving through space, but rather the space itself expanding. So that's how we get to the Big Bang, and that's the only way we can interpret this thing that Hubble saw, which was that objects twice as far away tend to go twice as fast away from us. So that's what the Big Bang is conceptually, and what we know is it created basically hydrogen and helium. And there may have been a little bit of lithium and beryllium. Those are the first 4 elements on the periodic table. But very, very small amounts of lithium or beryllium or any of those other elements, boron or whatever. It's pretty much just hydrogen and helium. So if I tell you the Big Bang created the universe, and we look at a periodic table that has over 100 elements, and I can only account for a little bit of 2 and a buttload of 2 of the 2 other ones, then we got a lot of explaining to do. So the Big Bang doesn't explain all the matter and energy in the universe and all that stuff. It can only explain the hydrogen and helium and the space itself. So the big question, and you'll learn this from that video when you get a chance to watch it, the big question is, where did all those other elements come from? And where did life come from? So the big idea on that is there turns out to be something called nucleosynthesis. So basically, a star is a nuclear fusion reaction at its core. In fact, a cloud of gas and dust basically becomes a star at the time at which the innermost, deepest part of it is so densely packed that the temperature reaches about 10 million Kelvin. And when it reaches that 10 million Kelvin, that's fast enough to force all the individual atoms, electrons can fall off because it's so energetic. These things are ramming into each other. The electrons are getting bumped off. But hydrogen itself, without any electrons, will have just be 2 protons, 1 proton for one hydrogen, another proton for another hydrogen atom. And boom, at 10 million Kelvin, the speeds are fast enough that they can actually run together. And here's a weird thing. They repel. They're both positive particles, and light charges repel. But at that speed, you can get it going fast enough where they can get so close that this other force comes in, and that's called the strong nuclear force. And when that happens, that strong nuclear force can bind them by turning one of them spontaneously into a neutron. So literally a proton becomes a neutron. And it shoots off an antiparticle of the electron to conserve charge. It also spits off a neutrino. And then another particle, just like that new one, will ram into that one, and a couple other protons will come in, and that gets us closer to, it actually gets us to the hydrogen nucleus, but missing one neutron, and then another one will come in, and finally we'll get a helium nucleus. So that is what's going on inside the core of the sun. Well, as the star gets older and older and older, it's eventually going to run out of that material that's in that core. Remember, that core is the only part that's really hot enough to fuse things. So if all the hydrogen inside that core has burnt and we don't have anything left in there except for the helium that's been made, then immediately it'll start burning, and all the weight of all the matter on the outside of the star will squeeze that core. If there's enough mass, that core will jump up to the next critical temperature, which is 100 million Kelvin, and that helium will then start burning itself. And that helium burns into carbon and some other things. And again, it repeats itself over and over again. As long as you got enough mass, it'll keep running out of fuel and keep generating treating some of that ash, some of that stuff that burnt from the previous fusion reaction. It'll burn some of that into other elements and into other elements, and it makes these sort of shells like a gobstopper. I don't know if you ever had a gobstopper, but it's like candy, and it starts off red. You suck on it a little while, it's blue. You suck on it a little while longer, it turns green. Well, that's what the star ends up like. It's basically got this inner core burning something. Right outside of it's maybe silicon. Outside of that, it's nitrogen and all sorts of stuff. Or well, it's actually not nitrogen. But anyways, there's a bunch of different elements being built up. And then that last most element is basically just some helium burning around the outside edges. And by doing that, you can generate most of the elements in the periodic table. Not all of them, but most of them. What we then know is once you get to the very bottom, the very last fusion reaction that goes on at the core, burns an element and creates creates iron. When that happens, it turns out there's no way to fuse or fizz. Fusion is when two small atoms come together or nuclei come together and make a bigger one. And fission's when one big one breaks apart into two smaller ones. The sun has fusion. So when two of these nuclei come together and form a iron nucleus, there's nothing that can be gotten from that gives off more energy than it takes in. So iron's the dead end. If it's massive enough, though, then that gravity will crush it. And we don't exactly know how all this stuff happens, but we know that it will crush it. And then we think a bunch of neutrinos will shoot out. We'll learn about those particles later. And that will cause what we call a supernova explosion. That supernova explosion makes enough energy to create the rest of the elements that we're missing from the periodic table. So we can only get the hydrogen and helium from the nucleus. Like I said, a little bit of lithium and beryllium, maybe even some boron or something like that, but generally just hydrogen and helium. But the life cycle of a very massive star can lead it to create all those different elements. And then the supernova explosion not only creates the remaining elements that we were missing, but it also blows all that stuff all over space so that other clouds, other gas clouds that form stars and star systems can form basically new star systems with these new elements. And now that you have these new elements, and some of them are very important, for instance, iron, we obviously need that for life, or for our life, because iron's in our blood. Carbon, that's some of the stuff that's not created in the Big Bang there, that's created, I mean, in the supernova, it's actually created on the way up there. A lot of other things as well. But for instance, the gold and the silver, and platinum, stuff like that, that's kind of expensive, all those materials were created in the actual explosion itself. So if you have a gold earring or maybe a silver necklace or something like that, you know that silver necklace was once inside, or that those atoms were once inside of a star, and that star exploded and created these new silver atoms or these new gold atoms. And that's partly why it's so rare, whereas all the other ones we can get other ways. Now, that answers the question about all the elements. The last part, though, is kind of weird. Turns out you need the really super massive stars to create all the elements necessary for life and for jewelry and all that stuff. But they live a very short period of time. So if those are the only stars you had, you wouldn't have enough time for evolution and the origins of life to create life itself. So it just turns out that these low mass stars, which aren't big enough to create much more than maybe carbon, those low mass stars like our own, in fact, have a life expectancy of tens of billions of years. And that gives us enough time for an origin of life, which we don't completely know exactly what the origin of life was or how it happened, but it does allow the mechanism of evolution to do its work long enough that life could be created. So it's kind of neat. It's like you need all these certain things, and we just happen to have all those right things to create the universe, and that's happened to be what we have. So that's sort of a quick, explanation of what the Big Bang is and how we explain everything that's around here. We'll get to more of that as the semester goes, but that's normally what we do in my very first talk, is we talk about the Big Bang, the scales of the solar system, which hopefully you saw in the other video, and stuff like that. So now that I've got that out of the way, the other thing, and do you have any questions, Addie?
No, I don't. I'm good.
Okay. Any of that sound familiar to you? Any of that sound like what you thought the Big Bang was, or had you never heard of the Big Bang?
I did. I just never really paid attention to it.
Yeah, it's very complicated, and I remember I'd heard a little bit about it like when I graduated high school, and didn't, like you said, I'd never really thought about it. But it's kind of neat just to think about, and you'll see in the video that in fact the Pope at the time actually embraced the idea when Lemaitre had suggested it. He said he saw that as what he thought Genesis was trying to explain in the Bible. So it's really weird how we've gone completely backwards from where we were to people thinking, oh, this idea of the Big Bang, that sounds like, God, and we're trying to pull the Bible into science, whereas now they think it's trying to take God out of science. So I always like to point that out because there's a lot of times where it seems like science and religion are doing this in astronomy, and it doesn't have to be. That's the main reason I bring that up. So next, I want to talk a little bit about the celestial sphere and the ancient Greeks and that sort of thing. So if you go out one night and look at the sky for an extended period of time, you'll be surprised if you actually pay close attention to stuff. I mean, literally spend a couple hours out there. You'll notice there's a star that sort of doesn't really move at all, and then all the other stars move, and you sort of think stars just rise and set and stuff like that. So maybe you look to the east and you expect a star to rise, and you look to the west and you expect a star to set. That's not how it happens at all. It's actually quite a bit weirder than that. In fact, there's one star, it's called the North Star, we also call it Polaris, that happens to be almost directly over our North Pole. And it is actually moving, it's just not easy to notice compared to how much all the other stars move. But because it's directly above our North Pole, and we know, for instance, our Earth is, rotating about that axis that goes through the North Pole and the South Pole, because of that, that star is right along that axis. So it's sort of like looking at the center of a CD or a record, and as it spins, the center doesn't look like it's moving at all. That's what's happening with the North Star, is it look like it's not moving at all. So just looking at that, and if you did that year in and year out, you would see that the shapes of certain stars, you can group certain bright stars in the same part of the sky together and say, oh, wow, that really looks like a big ladle, for instance, and that would be Ursa Major. And this looks like a little ladle with the handle bent the other way, and that would be Ursa Minor, or the Little Dipper. So Ursa Major is the Big Dipper, Ursa Minor is the Little Dipper. And you might see something that you thought looked like a lion, and that would be Leo. And if you watched it for weeks and weeks and weeks, you'd see that it never changes shape. Yet it still moves just like it's something rotating around us. So the ancients came up with an idea that perhaps we were at the center and that the universe was sort of spinning around us like that. That pretty much held for a long time, and everybody had this wonderful idea. But then when people started paying closer attention, they would notice something weird. So I'm going to share my screen, or share my document cam with you again to show you what was kind of weird. So I use this little top piece of paper up here that I haven't used yet with the Big Bang thing. So maybe you look up one night and you see a constellation that looks like this. So it's this star, and this star, and this star, and this star, this star, this star, and this star. So some people might recognize what this constellation is. It's supposed to be Gemini, okay? And you can sort of see why it's called Gemini. Well, one year you go out at night and you look up and there's a new object in it. You're like, what the heck? But all the other nights it was basically these groups of stars there, and that guy wasn't there. And then one night this guy wandered into the scene. Well, if you watch it, what you realize over weeks, and I'm saying all this stuff is moving and is getting in different positions each night, but just comparing this object's location to these objects' location, what you'd see over time is it would go here, and then here, and then here, and then here. And then as it got over here, it's getting brighter and brighter. That's why I drew it bigger and bigger. And then it would do this. And back where we started from, going around like that. So it was as if this thing wandered through that constellation Gemini. And in fact, if you'd watched it earlier, it would have come from this way and did this. Okay. So the Greek word for a wanderer was planetos, hence we have the planets. Those were the things that didn't stick together like all the other things that looked like they were, painted on the inside of a giant sphere. So that gave us the idea of the celestial sphere, and that's what we're talking about now. So if you look and see, there's the Earth, and we're looking at it with the North Pole up, not like where we would be standing on it. When we're standing on it, we have to have vertical up for us, and we'll draw that diagram later. But now if I take the Earth and imagine that there's a sphere centered on it, so here's a giant sphere that's centered on the Earth. Right above the Earth's North Pole is something called the celestial North Pole. So that's the North Pole of the celestial sphere. And right below the South Pole is the celestial South Pole, or CSP. Okay. Not only that, we can even use our same coordinate system. Do you know what this line right here is on Earth?
The equator?
Yep, that's the equator. And what do you think a line like this would be called on the celestial sphere? Can you guess?
Well, the same thing.
Yeah, celestial equator. That's exactly it. So that's your celestial equator. Okay. And of course you have, all these things we call meridians, and then we have lines of latitude like this. So it's probably wise for us to create a system of lines like that for coordinates as well. And in fact, if we go through Great Britain, there's one very special meridian called do you recall that one? What that special meridian's called? It's really cruel to do this to you. You're the only student in the class, so I repeatedly call on you. It's called the Prime Meridian. And it goes through a town in Great Britain called Greenwich. In fact, they make a big deal out of it. If you actually look at photos, they actually painted a yellow line through the city and all that good stuff. Well, that's the zero of coordinates, if you will, for the longitude system. So if you're on that line, anywhere on Earth on that line going through Greenwich, then you're at 0 longitude. If you go this way, you have a west longitude, and it goes all the way up to like 180. If you go the other way, it has a eastern longitude, and it goes all the way up to 180, that sort of thing. So that's sort of the idea of the coordinate systems on the Earth for longitude and latitude. Those are all sort of half great circles. These lines are more like rungs on a ladder, and they're latitude. I'll give you that young rungs on a ladder explanation so you won't forget which one's latitude and which one's longitude. Well, we're going to do the same thing here, only our prime meridian would go through here, and we make it a very special place on the celestial sphere. Just like we had to make it a very special place on Earth for the prime meridian. Specifically, Great Britain was the superpower of the time, so they took their city and ran it through there, and they called it the Greenwich, basically Greenwich time, and that's where the prime meridian goes through. So in this case, we wanted to find something celestial, something that occurs to give it a 0 of coordinates. And actually, I was going to put it there. It doesn't work very well for me there. Here's another line that would go straight down here, and as you go over here, it would be like this. I think this might be a better line for me to put the 0 of this coordinate system on. And it's a weird sort of coordinate system in that we don't use degrees or anything like that. We actually use hours, so it's kind of odd. But this will be it right here. We're going to call this where this line intersects the celestial equator. That is basically part of what we call the ecliptic. It's the path that the sun follows throughout the year. So if you watch the sun for a year, it appears from our perspective that the sun actually crosses our celestial equator on a very specific day. It's roughly 3/21 every year. And that's actually called the vernal equinox. Equinox means equal night. So they're basically talking about equal night and equal day. If you watch it further, from those days on, it gets higher and higher in the sky. Higher and 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 higher until it reaches its maximum height right here. And that's roughly 6/21 or 6/22. It might even be 23. It varies within a day or two. If you watch it further still, it comes back around, getting lower, 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 and then hits the equator on the backside this time on roughly 921. And then it gets lower and lower and lower and reaches its lowest point roughly, I won't say it like this actually, roughly here, and that's roughly 1221. That's a really terrible drawing, but that's basically, it should have looked more like just a big oval, but when I made it in 2 dimensions instead of 3, it made it a little messy. So we now have this wonderful celestial sphere. I didn't take as much time to make a good circle on that one. I'm going to make the Earth a little smaller now. But you remembered how, this was the West Coast, and this is the East Coast, and Florida, and so on and so forth. This is the North Pole. This is the North Celestial Pole. This is the South Celestial Pole, and this is the South Pole, so on and so forth. I'm going to draw it in 3D now. And you'll see this is the equator, the celestial equator. And that's it going around the back. Okay. And what I'm saying is roughly 321. That's when this happens. And the sun goes this way, 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 this way. And it gets higher and higher and higher. And then right about there, which is roughly 621, that's the summer solstice. And then it starts getting lower, 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 lower. And that happens right about here, which is roughly 921. That's the autumnal equinox. This one was the vernal equinox, don't forget. And then it gets lower and lower and lower and lower and lower and lower still until it reaches a maximum lowness right here. And that's roughly on 1221. And that's basically the day, or the origin of the coordinates. So we call this sort of prime meridian, if you will, we call that 0 hours right ascension. So it's 0 hours right ascension. Again, I went crooked on that. That's supposed to be a lot smoother. It would have been nice if I put this right there and then they're like that. Yeah, now it's much more beautiful. Anyways, so that's the path that the sun appears to follow in this grand celestial sphere. And then the constellations are sort of just painted on it. And notice it says 0 hours right ascension. Right means going to the right that way. And ascension means going up. So oddly enough, from where we go, where we're looking right now, as if we're God on the outside of the celestial sphere, as we go to our right, 15 degrees, then we'll get to 1 hour right ascension. If we go 30 degrees, it's 2 hours right ascension. If we go 60 degrees, it's 3 hours right ascension, and so on and so forth. And in fact, once you get a quarter of the way around, what's a quarter of 24? That turns out to be 6. So at 6 hours right ascension, we have the summer solstice. And then at 12 hours right ascension, we have the the autumnal equinox. And then at 18 hours right ascension, we have the winter solstice. And then back again at 0, we get the autumnal or vernal equinox, excuse me. So that's how the celestial sphere works. We can get from that some neat information. So I'm going to draw a little graph real quick of what that tells us. If I make a graph like this, and I cut it in half, and I cut each of those halves in half, it turns out, let's call this line right here the celestial equator. That's the celestial equator. That also happens to have a coordinate of its own, just like we had right ascension coordinates. This has a coordinate of 0 degrees declination. If I go that way, they're positive, and if I go this way, they're negative declinations. Okay, so as I go from here to here, just like with latitude, I go, 15 degrees north, 23.5 degrees north, that sort of thing. And down here, I go 15 degrees south, 23.5 degrees south, all that stuff, all the way down to 90 and all the way up to 90 north as well. 90 north being the North Pole, 90 south being the South Pole. Positive 90, of course, being the North Celestial Pole, and minus 90 being the South Celestial Pole. Now, with that in mind, it turns out this little path, the ecliptic that the sun goes through, never gets more than 23.5 degrees approximately away from the celestial equator. So this side is going to be positive 23.5, and this side will be negative 23.5. And if I say this is a right ascension of 0 hours, I know that occurs on a date of 3/21 roughly. So I can actually plot the path of the sun, and it goes like this. So that's 6/21. That's 9/21. Of course, that also corresponds to 6 hours right ascension. And this corresponds to 12 hours right ascension. Then it reaches all the way down here to negative 23.5 on 12/21. And that corresponds to 18 hours right ascension. And then it comes back to 0 declination again. This is the same date as over there, so it's 3/21. And it's also 24 hours right ascension, as well as 0 hours right ascension. So that little graph tells us how to find the coordinates of the sun at any particular time in the year. And if you actually, did a curve fit with a graphing utility or something like that, if you, want to play with math, you could actually make out a fairly accurate prediction of the right ascension declination of the sun throughout the year. But the main thing is I want you to be able to answer questions like, what's the right ascension on 6/21? What's the declination of the sun on 9/21? What's the right ascension of the sun on 3/21? And then in a multiple choice type fashion, I could say, what is the right ascension and declination of the sun on, let's say, 9/26? And I'd have answers like 0 right ascension, or 0 declination, 12 hours right ascension. I would have, 12 hours, 2 minutes right ascension, and a declination of positive 2, or the same thing, but with a declination of negative 2, or something like that. So I can get you to figure out whether it's going down or up from one day to the next. Even though you don't precisely know what that figure is, I can make up one, and the best answer would be the right answer. Even though it might not be exactly true, it's going to be the right answer. So knowing this helps you a lot. When I draw another diagram of the celestial sphere, it's going to help you even more. So this diagram is extremely important. A better version of this you can see in your textbook, for instance. But anyways, that's fairly helpful. Now, what I'm going to do is take another sheet of paper that I have right here and draw that flat version of the Earth with the celestial sphere around it. Only this time, I'm going to tilt the Earth. So here's the equator. And here's the North Pole. And here's the South Pole. And this right here is roughly, let's say, about 35 degrees. 35 degrees is roughly where we are in North Carolina. So I'll put a little person standing on top. That's why I had to tilt it. I had to tilt the Earth so that up meant up for us. Now I take and draw my celestial sphere again. Okay. Again, the celestial equator. I should use green because I used it before. So the celestial equator would be right over top of the Earth's equator. So it goes like that. Now, of course, the celestial sphere is ginormous. You know, the nearest star is 4.2 light years away. And, you know, we're like 0.00000000000 light years in radius or something. So it's like really, really small. So this should be infinitesimal small, which means the person standing on Earth's horizon is in fact right here. So that's your horizon if you're standing there on top of the Earth. Of course, directly overhead is called your zenith. And directly below your feet is called your nadir. Like that. And Addie, like I said, it is optional that you're here. So if you need to go or whatever, you don't have to stay. I'll understand completely. I'm going to continue covering this and recording it though. Okay.
I'm okay. I'm listening.
Okay, awesome. Appreciate it. So there's your nadir and there's your zenith. Now, from this diagram, we can get a lot of cool stuff. See, this angle right here from the celestial equator up to the line connecting to you, that angle in there is your latitude. And in fact, since I went towards the north side, I'd say your latitude's roughly north 35 degrees. Okay. So I can use that. I know that this whole angle right here is latitude. So I'm going to write it, instead of saying the special case of 35 degrees, I'm just going to call it L for latitude. Okay. Now, you know this line points straight up, and this line is horizontal, so the angle total here must be 90 degrees. So for instance, if this one's 35, then this one must be 90 minus 35. So we'd end up getting what, like 55 degrees over here? So this angle would be, in our diagram, it would be roughly 55 degrees. But for any latitude, just like we found that, we did 90 minus the latitude, so it'd be 90 degrees minus L. So this is a formula. It's the formula for the elevation of the celestial equator. So I'll say elevation celestial equator. That's what that is. So if you want to find the celestial equator in the night sky, you turn to the south, because remember the North Pole is pointing this way, so this person would have to turn facing that way. When he turned facing that way, if he then looked up into the sky above the horizon, estimate where the horizon is, and look up 55 degrees for our location, he would know that's how high the celestial equator is. Now, the helpful part about that is, remember, that's what this green line is. That's the celestial equator. So if you want to know the height of the sun on a particular day, well, you know the celestial equator for our latitude is already 90 minus 35, which is 55 degrees. But if I say, how high is the sun on 321, I look and I say, oh, well, the declination is 0 on 321. So it's actually on the celestial equator. So I know the sun is only 55 degrees high on 321. However, if I asked a more complicated question, what is the elevation, or altitude is another word for it, by the way, the altitude of the sun on the summer solstice? Well, then you say, okay, well, the summer solstice, that's 621. Oh, yeah, it's up 23.5 degrees. And that's why we have the Tropic of Cancer and the Tropic of Capricorn, for instance. But it's up 23.5 degrees above the celestial equator. So I look over here and I say, well, I know the celestial equator is 55 degrees up. So I add 23.5 to that, I get 78.5 degrees. So the sun's going to be up 78.5 degrees on 621. So for L equal 35 degrees, sun's altitude equals 78.5 degrees south, above south, I should say. At noon. So that's going to get us some information. For instance, the fact that it's 78.5 degrees means the rays of sunlight are coming down nearly perpendicular to the surface. So a given ray is only going to spread out over a small area. But if you tilt it a lot, then that ray is going to have to spread out over a large area. So that means the sunlight is less intense. So when the sunlight is coming from a lower height in the sky, the sunlight is less intense. It's spread out over a large area like this. And when it's coming straight up and down, in fact, it'll be held over a circular area like this, and it's much more intense. The same amount of light in this circle as there was in that one, but this one's spread out through like a big ellipse. So that's actually the reason for the seasons, if you will. We have summer because the sun is higher in the sky. We'll also figure out that that also means the sun's up more during the day. In other words, daylight's longer. So you combine those two, and it definitely gets warmer during the summer and cooler during the winter. And it also explains to you why the higher your latitude, remember the bigger the latitude is, that is actually meaning you're getting this angle right here closer and closer to your horizon. So the sun's not going to be able to come up very high at all. And in fact, it gets colder. So that's why the winter circle and stuff like that, for instance, is quite cold. And in fact, has a whole half a year that you don't even get to see the sun. So that's kind of neat. If I continue on with this, working this out though, there's another angle I can find that's very important. For instance, notice if I follow up along the Earth's axis of rotation, I'll run into the North Celestial Pole, right? That's roughly where Polaris is. It misses a little bit, but it's pretty close. But look at this. This angle is the equator for the celestial sphere. This angle is the axis of rotation for this celestial sphere. So they're actually perpendicular. That means this angle from here to here is 90. So this angle has to be 55, just like that one was. And in fact, this angle from your horizon up to the North Star roughly is in fact back to 35 degrees, because this plus this has to be 90 again. So since this was 55, this one must be 35. So this angle right here would be 35 degrees for our special case. But for the general case, this angle from here to here is your latitude. So if you're out at sea and you want to know what your latitude is, you just, especially at night, you just use a protractor, look at the horizon, and measure using that protractor the angle up to the North Star, and that'll give you your latitude. So that's another important formula, if you will. This is your latitude. If you look to the due north, measure up from the horizontal up to the North Celestial Pole, which is essentially Polaris, then you'll get the latitude. The way you normally do that, by the way, is you can just take a protractor, and some people will actually take and mount a little straw on the end, so they're forced to look straight along the edge. But you look right through there at the North Star, and then you hang a little mass through the hole in the protractor, a little weight like that. And it's got to be a symmetric weight so the string don't go crooked or anything. And this angle right here is what you're looking for. And you can tell that this angle and this angle, this is roughly, well, you can find it mathematically how this angle relates to that angle. And when you do that, that'll give you your latitude. So that's another neat thing we can use. So we've learned a couple things. We've learned that one, the sun follows this neat ecliptic, as we call it, because that's where the ancients discovered that when the moon was on it, you could have an eclipse. So they named it the ecliptic. And that allows us to determine the elevation or altitude of the sun relative to the celestial equator on a given day. And then we discovered that the celestial equator is up a height 90 minus L. So for instance, if you're at somewhere 20 degrees latitude, then this would be 70 degrees. And this would only be 20 degrees over here. So that's kind of interesting. But another thing we can do is remember the Earth is actually rotating this way, right? Remember, this is the West Coast, this is the East Coast, so on and so forth. We know that the Earth is rotating that way, but we envision the celestial sphere as rotating this way. So this top part's coming out and going like that. Well, if you imagine this person sticking their arm out like this, just on the inside of that celestial sphere, what you'd see is as this celestial sphere rotated this way, that person's arm, if they're looking this way now, stuck their arm out, their arm is going to go in a counterclockwise direction while they keep it on that celestial sphere. Because of that, we can tell what direction stars are going to move. And in fact, if he stuck his other arm back here, of course, he'd have to be able to tear through the Earth and everything because there's your horizon. What he would actually get is that it goes in a clockwise fashion on that side, because if you look this way, when the Earth is doing this, if you're looking this way, then you're seeing it rotate this way, which is in fact clockwise. Okay? So what can we do with that? Well, we can do something really neat. I can, for instance, draw the horizon. There's a horizon. This will be north. If you go out to the Outer Banks, for instance, and you look due north on the beach, you know the ocean will be on your right, and you know the dunes will be on your left. So to the right of us is east, and to the west, to the left of us is west. And now we know that special star right above due north is Polaris, and actually Polaris is the end of the handle of the Little Dipper. Okay? So what we know is going to happen is these stars are all going to rotate in a counterclockwise circle. About the North Star. And if I keep following that, remember this celestial sphere is supposed to be this rigid sphere, if you will. So all parts have to move exactly the same way. So all these lines are going to be parallel to one another. And all of a sudden, remember, this is this way, and 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 this is this way. What it tells you is answers to a lot of different questions. For instance, if I see a star due east and I wait an hour, in which direction or directions will it have moved? I'll give you choices like up, down, left, right, up, left, up, right, down, left, down, right, or not at all. Those are typical choices I'll give in this type of question. So if I see a star right here directly above the eastern horizon at 8 p.m., and I come back at 9 p.m., in which direction out of all these choices do you think the North or this star would have moved? Can you tell from that green arrow?
Is it up?
It's definitely going to move up because you see the arrows going up. But is it only up, or is it up into, say, a left or right?
Up to the right?
Exactly. That's exactly the right answer. So up and to the right is the way it's going to move. You can also answer the same question for over here. If I see a star directly above the west at 8 p.m., in which direction or directions will it have moved at 9 p.m.? Can you tell which directions that would be? Do you think it's going to be down for starters? Or
Is
up?
that down to the left?
It's down. It's a common problem. Everybody gets that. Yeah, it's down to the right, actually.
Okay.
I think you just got your left and right mixed up. That happens to me all the time, too. So this one's down and to the right. Isn't that cool that we can predict stuff like that just by knowing that the celestial sphere is a model that works? Now, I can also ask 4 other questions, and I will. For instance, if you see a star to the right of Polaris, I could ask you which direction will it move in an hour, or if I see one above Polaris, or I see one to the left of Polaris, or if I see one to the right of Polaris. So those are the 6 questions I can ask you based on just this diagram. And I don't even necessarily give you that diagram. I'll just say, hey, I see a star at 8 p.m. In which direction or directions will it have moved at 9 p.m. if the star was in the west? I see a star in the east at 8 p.m. In which direction or directions will it have moved at 9 p.m.? Or I see a star to the right of Polaris, which would be like right there. In which direction or directions will it have moved by 9 p.m.? You think you can get that one, Addie? It takes a whole 24 hours to do all this. So it takes at least 6 hours to get there, another 6 hours to get there, another 6 hours to get there, and another 6 hours to get there. So it didn't go any further than maybe this. So can you think which direction it's actually going? Star right of Polaris.
Up.
Yeah, it's definitely up. And is it going to the left or to the right, or just straight up?
Left.
Exactly. So this one's up and to the left. Ain't that cool?
Yeah.
Now remember what I told you about looking to the south. We have another diagram just like that, but this is simple. It's only one question comes from it, really. If we're looking south, then we have this odd thing that east is over here, west is over here, and you already know that stars sort of rise in the east and set in the west. So you've probably already got the diagram figured out. It's basically a circle too, but it's a clockwise circle, and the center is way down here, below the horizon. So it reaches its highest point due south, and then comes this way. So in fact, every star, actually every object due south of you that's sort of in the sky, whether it be a planet, a star, a moon, or whatever, it's going to essentially move down and to the right. Okay, from again 8 p.m. to 9 p.m. So from that little celestial sphere, we were able to figure out that cool stuff, like, how high will the sun be on a particular day? How low will the sun be on a particular day? What's its right ascension and declination on a particular day? What direction a star will move if it's in the east? What direction will it move if it's below Polaris? All that stuff came from that one little diagram. It's pretty awesome. One other thing I want to talk about is all these things on the celestial sphere is going to move that way. And that includes, believe it or not, the moon, the sun, and the planets. But if you watch them more than a couple hours, or more than a couple weeks at least, you'll see that they are moving differently. So from hour to hour, they look like they're doing exactly the same thing as the stars. But if you watch them long enough, they really are moving a little bit differently. The inner planets are weird. Sometimes they're moving closer towards the sun. Sometimes they're moving away from the sun. But the outer planets are generally all moving in the opposite direction that the stars are versus the background stars. So, stars rise in the east and set in the west. So stars rise in the east, sit in the west. If you had a star and a planet, an outer planet like this, so this is the outer planet, this is the star. If it's rising, really what tends to happen, if you could watch it over several weeks, most of the time the planet will lag behind. In other words, it's going eastward. It's going towards the east against the background stars. Every now and then, remember that loop that I showed you that Planetos did? When it's doing that loop, it actually goes the opposite way. So it actually, for that brief period of time, it would actually pass the star, and then it would slow back down and go back this way. So that's really the only real exceptions. The sun moves sort of the opposite direction, as does the moon. The moon does so way more quickly than do the planets, and way more quickly than does the sun. But that's pretty much how everything moves in the night sky, or the sky in general. Just you can't see them during the day. The last thing I think I want to discuss in this particular video was a day. Okay, so we've seen that the Earth rotating is really what causes stars to move in general. And we've seen that the seasons are caused sort of by the elevation of the sun, and that's because of the tilt of the Earth's axis. When the Earth is on this side of the sun, if that dot right there were the sun, okay, then the bottom hemisphere is getting the brightest sun. When it's over here, the upper hemisphere is getting the brightest sun. So that's the summer for the northern hemisphere, and this is winter for the northern hemisphere. So that's the big reason that this seasons happen. But the other thing that's kind of neat is we can actually take this and go a little further and say, what does a day mean? So if I imagine this, let's make our sun red for obvious reasons. So here's our sun. And let's say this is Earth. And you probably think of a day as the amount of time it takes the Earth to make one rotation. So let's say we have a pole on the Earth that we're using. We're right on the equator. It's 321, so the sun's directly overhead. So that pole casts essentially no shadow. Okay. Now, if we just sat there, which we don't, we actually orbit as well or revolve around the sun as well. But if we just sat there and rotated, then of course the sun or the Earth rotating 360 degrees would make that pole have zero shadow again. That would be a day. But the problem is that's not what happens. As the Earth is rotating this way, it's also revolving this way. So what really happens is it moves over here a little ways. Now the Earth has made a 360-degree rotation with respect to the stars. And I'll say with respect to stars. Okay. But it turns out that's only 23 hours, 56 minutes. That's not our day. That's called a sidereal day. So that's a sidereal day. It's not the day that we're used to. And notice the reason. Clearly, the sun is casting a shadow over here on that pole. So what we got to do is wait a little bit longer. In fact, it's about 4 minutes longer. And then the Earth will have not only moved some more, but it'll move in such a way that that pole is sticking straight towards the sun again and have no shadow. So the Earth has to rotate through this angle every day. We know that it does 360 degrees rotation in roughly 365.25 days. And if you do that division, it's 0.986 degrees per day. That's how much the sun moves. So this is 0.986 degrees, or roughly, 1 degree. This day right here, this period of time from here to here, is in fact 24 hours. And it's called a solar day. It's the day that we use. Okay. So that's the solar day. And the solar day is characterized by a 360.981 degree rotation. And it equals 24 hours. A sidereal day is a 360 degree rotation, and that equals 23 hours, 56 minutes roughly. Okay, so that brings us to, we did 1, 2, 3, 4, 5, 6 questions here, 7 questions. And they were all like 8 p.m. to 9 p.m., but I could really do an infinity of them. So I could say 8 p.m. to 8:30. I could say 9 p.m. to 10 p.m., all sorts of stuff. But now I get a new 7 questions I can ask doing this. And this is the hard part. So I won't take you to task and ask you on the fly these rougher questions. But let's say we look and we see a star. I'll write it up here. Due east of us. At 8 p.m. in which direction or directions will it have moved at 8 p.m. the next day? Okay, so that's kind of a weird question. So I see a star at 8 p.m. I come back tomorrow at 8 p.m. Am I going to see it having not moved at all because it's going to be in exactly the same spot, or am I going to see it moved? So the problem is that day from 8 p.m. to 8 p.m. the next day is a solar day. So the Earth has rotated not 360 degrees like that, but 361 degrees like that roughly. So in fact, it would still be the same answer as 8 p.m. to 9 p.m. You would say up and to the right. Okay. Now, if I ask the same question, but instead I said, what about at 7:56 the next day? At 7:56 the next day, the answer would be not at all. Because that is a solar, actual sidereal day. The sidereal day is the time required for that star to go from here to exactly there again. So it will not have moved at all. So that's another type of question I can ask. I can say, what if I see a star at 8 p.m. here to the right of Polaris, and I come back tomorrow at 8 p.m., which direction will it move? You'll say up and to the left. I'll say, what if I see a star at 8 p.m. today, and I come back tomorrow at 7:56? Which direction will the star move? You say none. Or I say, let's try this. Let's say I won't do that. Anyway, so those are various types of questions I can ask you. There's basically 7 of them for like 8 p.m. to 9 p.m., but then there's 7 more for 8 p.m. to 8 p.m. the next day. Then there's 7 more for 8 p.m. to say 7:56 p.m. the next day. So you can do all sorts of neat stuff like that. Do you have any questions? Anything you'd like to ask me about that? That's a lot of material we covered in a short time. All right. Well, I think that's enough for one sitting. So I'm going to go ahead and let it go at that. We did a whole hour. A typical class would normally be an hour and 15 minutes, but I think this is pretty good. I got a good introduction to the celestial sphere. We were able to use the geometry of the celestial sphere to figure out how high the celestial equator is in the night sky. We were able to figure out then how high the north celestial pole is, and therefore Polaris is. So that gave us a way of determining latitude. We were able to figure out what the path of the sun gave us as far as right ascension and declination of the sun throughout the year. And we could use that combined with our knowledge of how high the celestial equator is to figure out how high the sun is at noon on any of those days, specifically the equinoxes and the solstices. By the way, solstice means the sun stood still. It's solus and stis is a reference to standing still. It was as if the sun stood still because it was the longest day, if you will. So if you don't have any questions, I'm going to go ahead and call it. And I appreciate you showing up, and I appreciate you sticking around. That was awesome. It's much better that I can do this when there's people here than me just talking to myself. So send me an email if you have any questions. Hopefully this will help you.
All right. Thank you.
You're welcome. Thanks, Addie. Bye-bye.